scenario is something here. So, the surface temperature will be very close to boiling point, because now obviously the flame temperature is much higher than the T infinity will be now equivalent to flame temperature, which is much higher than the boiling point. So, you will see that the surface temperature here will reach a closer value to the boiling point, but it cannot exceed the boiling point again. Okay. So, the problem in hand is nothing but it is similar to the droplet evaporating in a high ambient temperature environment. That is the difference yet. What is that? If you have a droplet evaporation alone, then you can see that the oxidizer will come to the droplet surface. The ambient fluid, which is the oxidizer, reaches the droplet surface, because there is no reaction. So, it reaches the droplet surface. However, when there is a droplet combustion, okay, and a flame zone prevails, it actually separates the gas phase into two regions. So, oxygen or oxidizer cannot now penetrate into the, so nitrogen inert can penetrate, but oxygen cannot penetrate into the across the flame to the surface. In the region between the surface and the flame, there will be no oxygen. So, oxygen is consumed in the flame zone and the products are formed, products of combustion are formed in the flame zone. So, that means that oxygen cannot come to this. Similarly, fuel which can reach the infinity, okay, y of infinity at a larger radius. Here there is none such that, like you have to see that the fuel is consumed in the flame zone. So, outside the flame there will be no fuel left. So, these are the two differences, but other than that you can see that when you see the inner zone, it is pretty much the evaporation problem, where instead of oxidizer, products actually diffuse into this zone, correct. So, if you see here, if say the inner zone alone, for example, you have a surface and a flame, and this flame is going to provide heat to the surface, products are formed at the flame, so that diffuses here. So, that is the gas which is diffusing here, and the vapors are generated from the droplet surface diffuse towards the flame, that is it. So, that scenario prevails here. So, in steady burning regime, even when a flame surrounds the droplet, as told you, the TF will be much higher than the boiling point in general. So, in that case, surface temperature is still few degrees less than the boiling point, it cannot exceed the boiling point. Okay. So, this is very important. So, and T infinity does not have any influence here, because it is now away from the flame zone itself. So, flame temperature will have the influence, plus we can say that the equilibrium burning, if it prevails due to steady burning, then you can say that the surface temperature Ts will be less than the boiling point, few degrees less than the boiling point. So, this is the characteristic of droplet combustion. So, you can see that we are assuming a one dimensional flame, which is spherically, which is adhering to the droplet surface at a distance, say RF, from the center of the droplet, and this, as the droplet regresses, basically you can see that the steady evaporation range is formed. Okay. So, now what happens is the say diameter of droplet is going to decrease and it is going to go to 0 value, then the flame will reduce to 0 value. So, till that some vapors will be there. So, first the droplet diameter will shrink to a 0 value. So, that is the lifetime. Then the flame, the whatever fuel which is left over, that the flame radius which is higher than the droplet radius, that will reduce to 0 value. So, that is the way we will see this, but everything happens at steady state. Okay. So, at any particular diameter, if you want to see the rate at which it burns, that will be the same at all the diameters. Okay. Now, let us do some simplified analysis of droplet combustion, simplified analysis, in which the assumptions are made. So, a lot of assumptions we are going to make. As I told you, spherically symmetric flame exists over a spherical droplet. So, again this assumption will make us to go only for a one dimensional analysis, radial coordinate. Then the burning process is causes steady. That means even when there is a regression of the droplet surface, at every time instant the burning rate is the same. So, burning rate is constant. Okay. Next is phase equilibrium prevails at the interface. That means there is a definite value of Ts and YFS. Okay, pressure is uniform and constant. Okay, these are assumptions very important. Then the reaction is represented by the global single step, that is 1 kg of fuel react with S kg of oxidizer to form 1 plus S kgs of products. So, this is the usual assumption what we make for diffusion flames. Then as I told you, the gas phase is now having two zones here, the inner zone corresponding to the region between the droplet surface and the flame, and this contains only fuel, vapor and the products. And the outer zone, which is after the flame, RF or equal to RF, will consist of only the products and the oxidizer. There is no fuel present there. And this, since only two species are present in any zone, in inner zone fuel and products, outer zone oxidizer and products, only two species are present in these zones, binary diffusion can be invoked. Okay. So, for example, in the inner zone I can say DFP as binary diffusivity in the inner zone. Okay. In the outer zone I will say DOP, oxidizer and products. That's it. So, this binary diffusion can be invoked. So, there is no need of creating any diffusion coefficient or anything. Okay. Then in order to get rid of chemistry, I assume that the flame is very thin and the chemical reaction or the kinetics is very fast, infinitely fast, and I do not take into account of the radiation, which is negligible. In fact, actually the heat addition to the droplet is predominantly to conduction only. So, we can neglect the radiation. Then what I have not done in the previous case, I have tried to do here, that is I am invoking Lewis number equal to 1 here, because I would couple the species and the energy transport. So, in order to do that, I assume that the transport coefficient, see for example, we can say the alpha is equal to D. So, actually this we can write basically as lambda by Cp equal to rho d. So, this is the driving force for the heat transfer and this is driving force for the mass transfer. I will say the driving forces are the same. So, then finally, I also assume that all the properties are constant. So, this also I assume. So, these are the set of assumptions which are made to simplify the complex problem of droplet combustion. The heterogeneous problem, please understand that here there is a liquid and there is a gas phase here, and you can see that the vapors come out here. So, that we have to understand, see we do not need to solve for the liquid phase, but we have to couple the condition from the gas phase to the interface. So, the interface actually the droplet surface or what I call interface, there we need some balancing conditions in order to get the value. So, as we got for the burning rate, we use the condition of the interface m dot into HFG equal to the conduction from the gas phase to the interface. So, similar conditions for coupling the interface and the gas phase is required. Since we are assuming that there is no flow within the liquid or the uniform temperature prevails in the liquid, which is fine after the wet bulb condition is reached, then liquid phase need not be solved. Okay. Now, yeah. So, these are the typical profiles what I want to generate by solving the equations. Okay. So, you can see this, I have clearly divided the regions of the into two, a thin flame at RF, a thin flame so that is at RF. Then you can see that from that there is a temperature decrease towards the ambient. So, this is asymptotically to reach the ambient temperature after a long time. Then you can see that in inner there is a definite temperature here Tf flame temperature and there is a definite temperature Ts, which is under steady condition it is constant. So, you can see that this decrease is there in this. So, exponentially non-linear decrease will be there in this. So, this is the profile for the temperature in the inner and outer zone. If you take the profile for the fuel, there is a definite mass fraction of fuel. So, once this is definite fixed, this is also fixed, correct. These are connected basically, Ts and YFS are connected. So, there is a definite volume for YFS, and you can see that YFS decreases to a 0 value at the flame. So, this is flame radius, at the flame radius it decreases to 0. Similarly, ambient oxidizer has a mass fraction of 1, this is mass fraction 1, ambient at the ambient oxidizer, which consists of oxygen plus nitrogen etc., has a mass fraction of 1. Basically, I am saying oxidizer and I am normalizing the mass fraction to 1. So, that asymptotically comes in and diffuses towards the flame, and it will be consumed on the at the flame surface. Where the fuel and oxygen are consumed, you can see that products are formed. So, mass fraction of product is 1, P is the product basically, and the product basically diffuses towards this zone. This is very important to understand because there is only one flux here. The product cannot dissolve into the liquid phase. Okay. So, product cannot dissolve into the liquid phase. So, it can only diffuse towards this. But if you see, it can be convected also in this direction basically. So, it has a flux in this direction. So, you can see the product can be converted also. So, in this we can say YF plus YP, and in this zone we can say YO plus YP equal to 1. So, these are the structure. Basically, these profiles I want to calculate. So, I am interested in calculating 5 unknowns here. They are surface mass fraction of the fuel, surface temperature, flame radius, the location of the flame for a given RS. Okay. For a given RS or the surface radius, I need to find what is RF, then the flame temperature, and the final thing which is very very important is the mass burning rate of the fuel at a particular RS. So, RS is fixed here. So, for a particular RS I am trying to do this, because whatever be the RS value, if the steady combustion occurs, then at all RS mass burning constant will be the same, like evaporation constant, there will be a burning constant. The burning constant will be the same, but the burning rate will depend upon the radius, that we can see later. So, these are the 5 unknowns I have: the surface quantities YFS and TS, the flame quantities RF and TF, and the mass burning rate. These are the things which we need, and I have clearly designated zones as the inner zone, where the radius is say RS is less than or equal to R is less than or equal to RF. That is this inner zone, and the outer zone is basically RF is the flame radius is less than or equal to R is less than infinity. So, you can go to any far distance. Okay. Then please understand, as I explained here, since the product cannot dissolve into the liquid phase, you can say that the product can reach droplet surface only by diffusion, and no net flow of products inward at the inner region is possible. So, product cannot have a flux in the inner region, net flux. Okay. So, that means say rho P Vp will be equal to 0, net flux of this product will be 0. Okay. So, that we have already seen in the Stephen problem also, we have seen that the gas B only comes into the column by the diffusion. Same way, because only flux present there, because it cannot go into this liquid phase, only flux present is from the surface to the ambient, correct. So, that is the flux what we have basically here. But in this case, after this there can be a convection also. Actually, there is a flux for this to go towards the infinity, because this flux basically will be added up from the convective flux is nothing but the fuel which is actually convecting the product. That convective flux will be important to the product also, correct. So, that will be shown here. Okay, now let us see the conservation equations. Mass conservation says that I have the surface of the droplet. So, this is droplet. So, now there is a mass flux which is coming for the fuel, which is nothing but the rho fuel, V fuel at the surface basically into area of the surface, correct. So, now this is actually constant. So, when I say steady evaporation, this is at a given RS, this is constant. So, now this is known to me, known to be constant. So, that means that at any radius, at any radial location, the mass flow rate, this is the only mass flow rate. So, mass should be conserved. So, at any radius, the mass flow rate should be same as the mass flow rate of the vapor from the droplet surface. So, mass flow rate at any radius is equal to the fuel flow rate, or I will say fuel vapor flow rate from the droplet surface. So, that is the conservation of mass. Okay. So, this basically, if say for example, if the ambient fuel also can go into the liquid and condense and go into the liquid phase, then I cannot say this, because there will be a opposite direction transport also, where the ambient gas also goes into the liquid. But here, since gas cannot dissolve in the liquid, we can easily say that the only convection is due to the evaporation, Stefan's velocity, that will induce this. This is Stefan's velocity. So, rho into that velocity in the area of cross section will give you the mass flow rate. Okay, so, this is the conservation of the mass, the entire mixture mass. Then species conservation, as I told you, we have to have, so let us take the inner region first. In the inner region, only fuel and the product are present. So, F and P exist, and net flux of P is 0. That means we can say that the see, this is the equation written for fuel, correct. For the product, what I will write is I will put 0 equal to m dot double dash F into Yp minus rho d into d Yp by dr. That is all. That will be the conservation of product in the inner zone. Okay. So, you can see that the mass flux, which is actually written as rho F Vf at the surface. Okay. So, this is the mass flux. So, this is the total mass flux. This is actually the total mass flux. So, this is the total mass flux, which is actually equal to the mass flux of the fuel alone in this case. So, this is fixed law. But for the product, I can say that the net flux of the product, this is m dot double dash P, which is equal to 0. So, that will be equal to the convective flux plus diffusion flux. So, the convective flux basically is contributed by the fuel alone. So, this is the equation for the product. So, that anyway, in the absence of that, I will find this, and using this I can write this equation here. I want to find this, so multiply this by the 4 pi r square. So, we get this equation for the mass flow rate of the fuel. Okay. So, this is the equation what I get, but it cannot be solved easily. So, I need to know YF profile, whatever we did for the problem evaporation problem, we have to do this. So, this gradient has to be calculated and so on. But anyway, I can solve this now. First order equation in YF I get. So, first order equation in YF I can solve this. So, this is constant. So, this is constant now. So, using this I can solve the YF profile. How? So, now boundary condition for the first order differential equation in YF, what you have written here, m dot f equal to minus 4 pi r square rho d by 1 minus YF into dyf by dr, this first order differential equation can be solved by using two boundary condition, when r equal to rs, YF equal to YFS. But YFS is a function of Ts, that you have to just to keep in mind. Now, let us assume that Tf is known. So, we will not worry about that now. We know that there are 5 unknowns. So, we have to somehow create 5 equations to solve this. So, what are the unknowns? Again we will see YFS, Ts, the interface quantities, and the flame quantities, radius and temperature of the flame, and the mass burning rate. These are the 5 quantities which you are interested in. So, we will take the equation. So, we will try to build 5 equations out of the conservation equations what we have. So, first we have taken the conservation equation of the fuel, from which we have generated a first order differential equation using the boundary conditions for the fuel at r equal to Rs as Yf equal to Yfs, and as at the flame r equal to Rf, Yf equal to 0. So, by using these two boundary conditions I can solve this. Now, again conveniently the properties term I write as Z, and the suffix f is given because I am saying that I am trying to put the constant for the fuel conservation equation. So, Z suffix f, fuel conservation equation, will be equal to 1 by 4 pi rho d. Okay. So, now if you use this and integrate the fuel conservation, you get the profile with one unknown constant here. Okay. So, this is profile. So, how will you calculate the constant? Then you use this one of the boundary conditions, that is at the surface r equal to Rs, Yf is equal to Yfs, then you substitute here to get the value, then get the value of C1 and update the value of the profile, correct. So when only one constant is there, one of the boundary conditions is enough for me to use. So use this to evaluate the constant. So when I say R equal to Rs, I will put this R equal to Rs here, and the YFS in the left hand side I will put as YF of R will be YFS. So once I put this, the only unknown is C1. I calculate C1 and substitute back to the profile. I get this YF R. YF at any radius will be equal to 1 minus YFS into exponent of minus ZF MF by R divided by exponent of minus ZF MF by RS. So this will be the profile. So you can verify the boundary conditions again, what we have done earlier. When you put R equal to RS here, this will be YFS. So this will be YFS. I am putting R equal to RS. So if I put R equal to RS, this exponent term will cancel out each other. So we will get 1 minus YFS, which will be equal to YFS. So that is correct. So when you go to other condition, where you put R equal to RF, when you put R equal to RF, YF should be equal to 0. Now from that, actually I do not need that boundary condition at all to solve this, because only one constant, but actually I can use this boundary condition to solve for MF, which is also unknown. So actually speaking, based upon these conditions, so for example YFS goes to 0 like this, correct? This is the flame zone. So YFS, this is YFS. From YFS value, YF value goes to 0 value here, this is 0. So based upon these two values, say for example, based upon Ts, this is a function of Ts. So based upon Ts, there will be a YFS value, and there will be this profile basically. So now I can, the mass burning rate basically can be an eigenvalue between the RF and this, correct? At RF, this is R equal to RF, this is RS, and this is the function of this R coordinate. So this is YF, okay. So now please understand that based upon the YFS value and RF value, MF can be an eigenvalue. So if you vary YFS, then RF also will vary, then MF also will vary. So this MF can be got as an eigenvalue between these two. So first boundary condition, R equal to RS, YF equal to YFS, I have used to create a profile for this. Now if I substitute R equal to RF in this, I know YF equal to 0, then I can find the value of M dot F. So applying the boundary condition R equal to RF, at R equal to RF, YF equal to 0, then I will get, actually I will not get I can get this as an eigenvalue, but anyway I will not keep that as the value there, calculate this. Either I can calculate MF using this, or in this case what I have done is I have calculated YFS itself. See, please understand that if you go back, in this equation unknowns or YFS, if you want to calculate YF as a function of radius, I have what are the unknowns I have? I have this and MF. These are the two unknowns I have, because ZF is constant and RS also I fixed already. So at any R, if I want to calculate the value of YF, I need these two quantities. So either I can use this equation to calculate MF, or you can use the equation to calculate YF. Basically, I am not going to use this to calculate only one quantity. This is one of the equations. I want to generate one of the equations to calculate one of the unknowns. So there should be 5 equations. So I have not created any equation till now. There are 5 unknowns here, 5 variables to be solved. So let us find one by one. So the first variable is YFS. So write this equation in terms which have 2 unknowns here, YFS and MF, M dot F. So I can use this to find any one and put the equation ready for us. So that is what I am trying to do, but I am actually putting the YFS in the left hand side. I can also do the other one, MF also could be put in the left hand side. So now I designate this equation as E. So this has 2 unknowns again, one of the unknown is evaluated as a function of other unknown, okay. So now if MF is known, then YFS can be evaluated. So this is the equation E, I am keeping this. So one of the equations is generated, correct. So please understand that out of the 5 unknowns what I want, I need to generate 5 equations. Now I have created one equation. Equation E is the first equation I have created. Okay, now let us do the inner zone alone we have done now, correct. Inner zone where the conservation equation of the species, in which the YF has been taken into account, okay. Now at the flame sheet, you know the mass conservation is what? mass of the fuel comes in. See, at the flame sheet what happens, fuel comes here, mass conservation, fuel comes in, then oxidizer comes in, and products leave, correct. So this is conservation. So MF and MO they are added and MP goes out. Now I know that from the equation 1 kg fuel plus S kg oxidizer giving 1 plus S kg of products, I can write that this equation as MF plus S times MF, that is nothing but M dot O gives 1 plus S times MF, this is the M dot P. So this you can write, okay. So now please understand the fluxes. So when I say this is fluxes, you can see that when I say M dot O double dash, this is in the opposite direction, the vector, no, so it's a vector, it is an opposite, so rho V, correct. So that vector comes in, so in the other direction, that is the negative or direction, and that will be equal to minus of S times M dot F this, okay. To understand now, if you take the magnitudes, here I am trying to take the magnitude of the entire mass balance. What is the mass of the fuel entering the flame, is the flame zone. So when I say mass of the fuel entering the flame, mass of the oxidizer entering the flame, the mass of the product produced at the flame. So that is the conservation. But when you see in the flux way, you can see you have to see the direction. So now you can see that fuel is entering in the radial direction, which is positive. Oxidizer is entering in the other direction. So I have put S times the mass flux of fuel, but that should be given a negative sign because this is entering in the other direction. When I say flux, when I say the mass flow rate, there please understand that I am only taking the magnitudes to conserve the mass, so the mass conservation, conserve the mass. But when I say flux, I need to take the direction properly. So you can see that the M dot double dash of O will be equal to minus of S times M dot double dash of F. For the products, fuel is going in this direction, products are also going in this direction. But flux, please understand why products are going in this direction. Product has no flux in the inner side. So this is flame, this is inner region and this outer region. So since the product only diffuses through the inner region, it cannot have a flux in the inner region, because it is, if it has a flux at this, then it should go into the liquid also. So it has no flux in the inner region. So this is not there for the products, okay. So the products actually can have a flux in the outer region. So you can see that M dot P, which is in the same direction as M dot F double dash, you can write the flux as 1 plus S into M dot F double dash as M dot P double dash, okay. So these two you should understand, and also this identity is there, Yp plus Yo equal to 1. So using this, the oxidizer conservation can be written like this. So M dot F, now you see the positive sign because the oxygen is coming from the other direction. So negative of negative becomes positive here. So again you can see this, putting this S plus Yo here to get this, okay. You can write this, so you can take the conservation equation and substitute this value, you will get this. This is the conservation equation for Yo. So first order differential equation for Yo. Please understand that rho d is constant, M dot F is constant here, S is also known, okay. So now you can solve this problem, separate the variables and integrate and solve the problem, but boundary condition has to be seen. So please understand that in the mass conservation, the overall mass conservation is the mass of fuel plus mass of oxidizer entering the flame zone will be converted into products. The flow rate are defined like this. So when you take into consideration of this reaction, mass flow rate of fuel plus S times mass flow rate of fuel, that is mass flow rate of oxidizer, will be this. But I am saying mass flow rate, then I only take the magnitude. But if I want to write in the fluxes, when you write the Coulomb equation, I should take into account fluxes. This is actually this. So this is total flux of this. I need to know this total flux into Yo minus rho d, okay, that is constant. So dYO by dr. So this is the equation I have from Fick's law, but I don't know M dot double dash here. So in order to write this, I am trying to do these assumptions and draw the conclusion. Once I know M dot double dash F, Okay, when I write m dot double dash O in terms of m dot double dash S, I know the value of that, so I can write this equation. So that is what I am trying to do here. So once I do this, then I get this first order equation which can be solved now.